In this lecture, let us discuss the inverse Z transform using partial fraction expansion method and long division method. So in the previous lecture, we discussed the inverse Z transform through the integral equation, okay, Cauchy's integral equation through something called contour integral. But anyway, as a DSP engineer in digital signal processing, we will not use that method, but instead of that we will use a partial fraction expansion method most of the time, and maybe sometimes or quite a few times we will use long division method. Okay, so let me start now with the partial fraction expansion method. And this method is very popularly used to find the inverse Z transform. Now in the previous lecture I told you that if you know the Z transform of del of n, then u of n r to the n u of n, then r to the n cos of n omega naught u of n, comma r to the n sin n omega naught u of n. Right, then you can perform any Z transform or its inverse Z transform. Once you know the Z transform of this, then you can do inverse Z transform very easily. We will see how we can do that using partial fraction expansion method. So let me explain this partial fraction expansion method through an example. Now the question is, find h of n such that the question is find not h of n, causal h of n, causal h of n such that the h of z is equal to z divided by z times z plus 2 z plus 2 divided by z minus 0.2 z minus 0.6. Okay, so this is a given problem. From this h of z I need to find out h of n through inverse Z transform, and the important point to note down is causal sequence. Causal sequence means it is right sided sequence. Causal means. So the first thing you do when you encounter such an expression is to express it as a ratio, express it as a rational function. So that is the first step, a rational function in Z inverse, not in Z inverse. But the given function is in terms of Z. Therefore, I need to convert the polynomial from Z to Z inverse. So I need to convert this numerator polynomial from Z to Z inverse, and the denominator polynomial also from Z to Z inverse. So if you look at the numerator and the denominator, you have second degree polynomial. So therefore what you do is you divide by z square both the numerator and denominator. Okay, so you divided by 1 by z square times z plus z, one second, z times z plus 2 whole divided by 1 by z squared times z minus 0.2 multiplied by z minus 0.6. Right, if you rearrange this equation, then it becomes 1 plus 2 times z inverse. In the denominator it becomes 1 minus 0.2 z inverse multiplied by 1 minus 0.6 z inverse. Okay, now you look at this expression. This h of z is given in terms of z inverse. So this is the rational function in z inverse. Okay, now you expand in partial fraction. So this I can write a divided by 1 minus 0.2 z inverse plus b divided by 1 minus 0.6 z inverse. So why do you write it in this form, a divided by something and plus b divided by something? Because you know the z transform of alpha n times u of n. What is the z transform of this guy? This is 1 divided by 1 minus alpha z to the minus 1. So therefore I need to write this guy to match this guy. So that is why I took the partial fraction expansion, a divided by this term plus b divided by this term. Now once I know the value of a and b, then I can invoke this formula to find out the inverse z transform. So if you can express, let's see equation number 1. So if you can express equation 1 in this form, in equation 2 form, then your job is done. Okay, the thing is let me write down, this is equation number 1 and equation number 2. Now if you can express equation 1 in equation 2 form, then your job is done. Okay, but only thing is you need to find out a and b. Okay, a and b are found in the usual manner. We know how to do that. Regular manner you can find out a value and b value. So a value is equal to 1 minus 0.2 z inverse times h of z. Evaluate at 0.2 z inverse is equal to 1. Okay, don't compute 0.2 z inverse is equal to 1. Therefore z inverse is equal to 1 by 0.2. 1 by 0.2 is no 5 like that. Don't compute. Or you don't compute z is equal to 0.2 like this. Okay, this and all tedious method. Okay, don't go that. Straight away you substitute wherever you find 0.2 z inverse, you substitute 1, or wherever you find 1, there you substitute instead of 1, substitute 1 by 0.2 z inverse. That's all. It's a very simple calculation. Therefore 1 minus 0.2 z inverse multiplied by h of z. So what is h of z? H of z is 1 plus 2 z inverse, right? Numerator, denominator 1 minus 0.2 z inverse multiplied by 1 minus 0.6 z inverse. Evaluate at 0.2 z inverse is equal to 1, right? So this term will get cancelled and this term will get cancelled. Now instead of 1 you substitute 0.2 z inverse from this guy, and similarly here also for 1 you substitute 0.2 z inverse. Okay, therefore this is equal to 0.2 z inverse plus 2 times z inverse in the numerator, and in the denominator for this one you substitute 0.2 z inverse minus 0.6 z inverse. So is it minus or plus? It is 1 plus. I think why did I make a mistake? Okay. I'm sorry, I wrote the question wrongly. This is plus and this is plus, this also plus. I copied the problem wrongly. Okay, so this is plus, this also plus. Okay, fine. Now 2.2 z inverse divided by 0.8 z inverse. So this is 11 by 4. 11 by 4 is 2.75. So A value is 2.75. Similarly, you can find B, and that B value straight away I'll write down the answer here, minus 1.75. So if you substitute these values, A and B values, in the above expression, then your H of C is equal to 2.75 divided by 1 minus 0.2 Z inverse plus minus 1.75 divided by 1 plus 0.6 Z inverse. Now if you look at the formula, alpha times alpha to the n u of n is equal to, if you take Z transform, 1 divided by 1 minus alpha times Z inverse. Now instead of alpha, I have 0.2 here, right? So therefore 2.75 times, I can write 1 divided by 1 minus 0.2 Z inverse minus 1.75 times 1 divided by 1 minus of 0.6 Z inverse. Now you can compare the formula. Now instead of alpha to the n, I have 0.2 here. Here I have minus 0.6. Therefore this is equal to 2.75 0.2 the n u of n minus 1.75. If you take inverse Z transform, then minus 1.75 times minus 0.6 to the n u of n. Why did I put u of n here? Because in the given problem we assumed causal h of n. Okay, we assumed it is causal. Causal means right sided sequence. Right sided sequence means it is multiplied by u of n. So h of n. So this is the Z inverse Z transform. Inverse Z transform, because you wanted a causal sequence. If it was not, then we would have a problem. Okay, so something else. Okay, so in the given problem we said causal h of n, that is why we multiplied by u of n. Okay, ROC is not specified, but ROC is specified in terms of the causal sequence. Okay, so an equivalent specification is given by the word causal, because you are asking for a causal sequence h of n. So if this specification, if causal is not given, okay, not given, then the answer to the inverse transform would not have been unique. Okay, the answer we worked out will be correct only if 0.6 mod of z is greater than 0.6. So causal sequence, either I can say causal sequence, or I can say mod of z is greater than 0.6. Both are equivalent statements. Either I can give the ROC like this, or I can give like this, causal sequence. So both are equivalent statement. Okay, somebody comes and says causal sequence h of n, or the ROC mod of z is greater than 0.6. Both are equivalent statement. So causal sequence and mod of z greater than 0.6 are equivalent statements. Either you can say causal sequence, or you can give like this. So the ROC outside of a circle of radius 0.6 specifies that the inverse transform will be causal. One of the two must be given. Okay, either the ROC must be given like this or like this. So I have another point to make. So we go back to the original no problem. What is the original problem which I gave you? This is z times z plus 2 divided by z minus 0.2 times z plus 0.6. So this we wrote in this form, right? A divided by 1 minus 0.2 z inverse plus b divided by 1 plus 0.6 z inverse. Now how do you know that these two terms are adequate partial expansion of this guy? On the other hand, if you make partial fraction expansion of this one, if you make partial fraction expansion of this, there will be a constant, right? So there will be some constant k times plus a divided by z minus 0.2 plus b divided by z plus 0.6, like that. But in this no constant term. Why is it so? If you straight away use this expression, then you will get a constant plus a divided by this term plus b divided by this term. Because at infinity there will be a constant in this expression. At infinity there will be a constant. Okay, and that constant will be equal to limit z tends to infinity z square plus 1 plus 2 by z. I am writing the same expression in this form. Z square 1 minus 0.2 z plus 1 plus 0.6 divided by z. This and that will get cancelled. Substitute z to infinity. 1 plus 2 by infinity divided by 1 minus 0.2 by infinity multiplied by 1 plus 0.6 by infinity. Okay, so this guy will go, this guy will go, this guy will go. So you will get 1. So there is a constant term 1 in this expansion. But if you look at the polynomial in terms of z inverse, there is no constant term. Because if you look at the same expression here, the numerator degree is less than the denominator. Okay, the numerator is 1 degree less than the denominator. If you look at this expression, what is the numerator degree here? 1. And what is the denominator degree? Here I have z to the minus 1, here I have z to the minus 1. So denominator degree is 2. So the numerator degree is 1 less than the denominator degree. Therefore, if the numerator also had another factor like this z inverse in the numerator, then there would have been a constant term. So please take care of this when you are taking the partial fraction expansion. So whenever the numerator degree is less than the denominator degree, then you will not have the constant term. Okay, so let us take another example. Suppose the h of z is equal to p of z divided by q of z. Now let's assume that the numerator degree was higher. Okay, for example, p of z has degree of 3 and q of z has the degree of 2, right? 3 and q of z degree is equal to 2. Then the partial fraction expansion of this guy will have a constant term, let's say k0 plus k1 z inverse plus p1 of z divided by q of z. Okay, now how do you find out these two guys, k0 plus k1 times z inverse? Go to the long division method. Using long division method, you can take out this constant term plus the first order term. Okay, take out k1 times z inverse and k0, and the remainder, let's say p1 of z divided by q of z. will be such that the degree of q of z is, again this is same as 2 denominator degree, but the degree of p1 of z will be 1. So you must look at the given function very carefully. So in this case your h of z becomes is equal to k naught plus k1 z inverse plus p1 of z divided by q of z. And the inverse is not a problem. What is the inverse of k naught? K naught times del of n. What is the k1 times z inverse? K1 times del of n minus 1. Using time shifting property you can find out. So finding the inverse of a constant or delayed by one sample is not a problem. So this is how you will take the partial fraction expansion. There is another simpling feature about this problem, which is that there was no repeated poles. So in this expression we assumed all poles are distinct. In case if the poles are repeated, then what will you do? Right, see the poles were like 1 minus 0.2 z inverse. What is the pole? Equal to 0. In the denominator you had this, right? And one more denominator is 1 plus 0.6 z inverse. So z is equal to 0.2 is one pole, and here z is equal to minus 0.6 is another pole. So these two poles are not repeated, they are distinct, right? So they were distinct. If they are repeated, if they have repeated poles, then what do you do? There is systematic procedure that we need to follow. Let's take a general case and try to understand when we encounter a repeated poles. Suppose g of z is some numerator, let's say n of z, divided by the denominator polynomial with pole p z inverse, but this pole p is repeated capital L number of times, and the denominator I have some other polynomial, let's say q1 of z. Now this q1 of z has distinct poles, but here I have repeated poles. So whenever you have repeated poles, then you need to take care of that in a specified manner. Okay, so q1 of z contains other poles. I mean q1 of z does not contain the pole at z equal to p. All of them have been taken care of. Now then, provided degree of n of z is 1 less than the degree of the denominator. What is the degree of the denominator? L plus degree of q1 of z. So this can be written as summation of, you take the partial fraction expansion ai divided by 1 minus p times z inverse whole power I. So for first order pole I have one constant, second order repeated pole I have another constant, like a1 divided by 1 minus p z power minus 1 plus a2 divided by 1 minus p times z inverse whole squared, right, plus a3 divided by 1 minus p times z inverse whole cube plus dot 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 plus a suffix l divided by 1 minus p z inverse whole to the l. So this whole thing can be written in this compact form, summation of I is equal to 1 to capital L, okay, plus n1 of z divided by q1 of z. Therefore there are capital L number of constants. So this guy contains capital L number of constants, a1, a2, a3 up to al. Okay, and here this is n of z and this is n1 of z, where this n suffix 1 of z is a reduced polynomial which you can take care of by partial fraction expansion, and then you take the inverse inverse Z transform, that what we did in the previous class, previous example. Now so this is not a problem. So okay, the same format that we did in the previous example, as like our previous example, no problem. But this is the new thing for us now. And this is also not a difficult. You can do it by taking help of the fact that n times g of n is equal to minus z times d of g of z divided by dz. So if you take account of this, then you can find a general formula for inversion of this guy. So we will come back to this a little later. Now the next question is, how do you find out the constants a1, a2, a3, a4 and all? So finding inverse Z transform is not a formula, not a problem. Okay, you can use this formula and you can find out the inverse Z transform. It's very easy. But the critical thing is, we need to find out the constants a1, a2, a3 up to al. So how do you find these ai's, the coefficients? Well, all textbook gives this formula. This formula is little difficult to remember. So generally I will not use this formula. Okay, so unless I am forced to, I never use it, but always it is good to know. Let me write down this formula for completeness. So ai is equal to 1 divided by l minus I factorial minus p to the l minus I power of l minus I, l minus ith derivative of 1 minus p z inverse l g of z. Evaluate at z is equal to p. So this is general formula to calculate the constants a1, a2, a3, a4 up to al. And this formula looks a little difficult to remember, looks horrible. At any step you can make a mistake. So generally what we do in our class is slightly different. So what I do is the following. So let me take an example to illustrate this. Okay, so I am sure you will find more convenient than differentiating, and the scope of making mistake in the following procedure is much less. So g of z is equal to the numerator polynomial n of z divided by 1 minus p times z inverse whole cube times 1 minus alpha z inverse. So here the poles are repeated 3 times, right? So assume that numerator degree is less than 4. Let's say the numerator degree is 2 or something, or 3, like that. So if the numerator degree is less than the denominator degree, then we call it a proper rational function. Numerator degree is strictly less than denominator degree, then we call it proper function, proper rational function. Okay, see, there is nothing improper about the other rational function. That is, if the numerator degree is greater than denominator degree, I mean exceeds the numerator degree exceeds the denominator degree, or in case numerator degree is equal to denominator degree, then this is called a improper rational function. Improper rational function. But there is nothing improper, but then this term improper has gone into the literature, and we are forced to use it. Okay, so nothing is improper here, but general name is improper rational function. Therefore, in this case, you can write now three constants: a1 divided by 1 minus p times z inverse plus a2 divided by 1 minus p times z inverse squared plus a3 divided by 1 minus p times z inverse whole cube plus b divided by 1 minus alpha times z inverse. Now we can find out b very easily, right? How will you find out b? B is equal to 1 minus alpha times z inverse times h of z. This product is evaluated at alpha z inverse is equal to 1. Okay, so do not bother about finding the value of z. Okay, no, alpha z inverse is equal to 1. This is good enough. And a3 can also be found out exactly. So a3 is equal to 1 minus p times z inverse whole cube h of z. Evaluate p times z inverse is equal to 1. So a3 is known and b is known. All that you have to do now is to find out what is a1 and what is a2. Obviously, if you want to apply the formula, okay, this formula, then you have to differentiate twice to find a2 and differentiate once to find a1. So instead of doing that, actually to find, so in this, let me write down. To find a2, 2 times you have to differentiate. 2 times differentiate. To find a1, 1 time you have to differentiate and then substitute through this lengthy big formula. But generally, what one will do is, instead of doing that differentiation, take 2 specific values for z inverse. This is an alternative method to calculate a1 and a2. So what you do is take 2 specific values and substitute. It's up to you, whatever the value you like it, you can substitute. Okay, now let's put z inverse is equal to 0 in the above partial fraction expansion. If we substitute z inverse equal to 0, then g of z equal to a1 divided by 1 minus 0 plus a2 divided by 1 minus 0 plus a3 divided by 1 minus 0 plus b divided by 1 minus 0. So when z inverse equal to 0, then z becomes infinity. Therefore, g of infinity is equal to a1 plus a2 plus a3 plus b. In this, a3 is known and b is known. Therefore, a1 plus a2 is equal to a3 plus b. Am I right? Minus g of infinity. I am sorry, I forgot the minus sign. G of infinity minus a3 minus b. So let me call this as one equation, linear equation. Okay, the other equation, how will you get? You substitute z inverse equal to any other value that you like. Put z inverse equal to 1 or z inverse is equal to minus 1. In case if you put z inverse equal to 1, then what will you get? G of 1 is equal to a1 divided by 1 minus p plus a2 divided by 1 minus p the whole squared plus a3 divided by 1 minus p the whole cube plus b divided by 1 minus alpha. If we substitute z inverse equal to 1. Once again I get an equation in the two variables, okay, a1, a2, because a3 and b are known. This is known and this is known. Therefore, a1 divided by 1 minus p plus a2 divided by 1 minus p the whole squared is equal to g of 1 g of 1 minus a3 divided by 1 minus p the whole cube minus b divided by 1 minus alpha. That's it. So this is my second linear equation. Equation number 2 and equation 1. You solve equation 1 and 2. Okay. So I have two simultaneous equations and I can solve it. So this procedure, although a little bit of algebra, much simpler. Okay, this is much simpler and not prone to mistakes. Well, if you want to make a mistake, then okay, nobody can stop you. So, but there are less chances of making a mistake in this procedure. I would suggest that you follow this procedure. In fact, you can do one more thing also. Okay, another method that one can do is don't follow this method also, but okay, so there is another method, so which is very not that much convenient, but if you do, you can use that. Okay, so do the following. So g of z is equal to a1 divided by 1 minus p z inverse plus a2 divided by 1 minus p z inverse whole square plus a3 divided by 1 minus p z inverse whole cube plus b divided by 1 minus alpha times z inverse. Now the left hand side, you know what is the thing. In the left hand side I have n of z divided by 1 minus p z inverse whole cubed times 1 minus alpha z inverse in the left hand side. The right hand side, rearrange this guy. Okay, so this is a1 times 1 minus p z inverse whole squared times 1 minus alpha z inverse plus a2 times 1 minus alpha z inverse times 1 minus alpha z inverse plus a3 times 1 minus alpha z inverse plus b times 1 minus p z inverse whole cube divided by divided by 1 minus p z inverse whole cube divided by 1 minus alpha z inverse. So in the left hand side you have numerator polynomial n of z and the denominator polynomial this one. Whole cube, then 1 minus alpha z inverse. Now both sides you can cancel. This guy will get cancelled with this guy and this will get cancelled with this guy. Now compare term by term from the numerator. Okay, this guy with this numerator. Now compare. So I get the polynomial in the numerator, that is a polynomial in z inverse with the constants a1, a2, a3 and b3 in the numerator. See, a3 and b are known. So a1 and a2 you have equal corresponding coefficients in the left hand side. Therefore n of z is equal to a1 times 1 minus p z inverse whole square times 1 minus alpha z inverse plus a2 times 1 minus p z inverse plus 1 minus alpha z inverse plus a3 1 minus alpha z inverse plus b times 1 minus p z inverse. whole cube. So you can do this method also if you find that to be more convenient. If you like this method, you can do it. Compare the term by term on the left hand side and the right hand side, so that you will get a A1 value, A2 value, A3 value and A4 value. Okay, this is the third method by which you can do it. And this one is the second method you can do it. And the first method is using this formula. So I don't recommend this first method using this formula because it is lengthy and there is a more chance to make a mistake. So let us employ the second method. So let us find B value. B value is 1 minus alpha times Z inverse multiplied by G of Z, which is evaluated at alpha Z inverse is equal to 1. Similarly, how do you find out A3? A3 is equal to 1 minus P Z inverse whole cube G of Z, where P Z inverse is evaluated at 1. Now that's how you will find out B and A3. Now can I choose Z inverse is equal to infinity here as one of the values? If Z inverse is equal to infinity, then all the terms, where are those terms? A1, A2, A3 and B becomes 0 because the infinity is coming in the denominator. If Z inverse goes to infinity, then Z goes to 0. Therefore, G of Z becomes G of infinity. Infinity? No, 0, right? 0. Therefore, G of 0 is equal to A1 divided by 1 minus infinity plus A2 divided by 1 minus infinity the whole square plus A3 divided by 1 minus infinity plus B divided by 1 minus infinity. So all the terms are vanishing here. So I cannot take Z inverse to go to infinity because the numerator degree was less than the denominator degree. So Z inverse is equal to infinity is not a proper choice. Okay, but Z inverse is equal to 0 is a proper choice. You can substitute and find the values. Similarly, Z inverse is equal to plus 1, Z inverse is equal to minus 1. These two things can be a proper choice. So these are the simple choices and this is usually does the job. Okay, so that's how you will approach the inverse Z transform whenever you have the repeated poles. Now the next method is inverse Z transform. Inverse Z transform, but now we are going to employ long division method. Okay, so the inversion of Z transform can also be done by long division. You see, all you have to do is to express this G of Z, which is a rational function, numerator polynomial divided by denominator polynomial, Q of Z, in the form of like G of 0 plus G of 1, Z inverse plus G of 2 times Z inverse, like this. So if you divide P of Z by Q of Z using long division and take the quotients, the quotient is a polynomial in Z inverse. So the coefficients will give you the sequence. But the difficulty is that you may not be able to find a closed form formula in this long division method. So if you don't get a closed form formula, then you may not be able to find in general a formula for G of n. So you can find the individual coefficients, fine. But how will you get the closed form formula for this? Even if it is sine or cosine, you may not be able to guess what the exact form is. Okay, therefore sometimes it is good and sometimes it is not. There are certain cases where you cannot apply partial fraction expansion. So in such a case, you can take the help of long division method, but not in all the cases. Okay, so that is the only problem. But we will take this also to illustrate the fact that the ROC is an extremely important attribute of the Z transform. So in this long division method also, this ROC is very important. Okay, now straight away I wrote like this. Now the question is this correct? Okay, because in the given problem it does not contain the ROC. Without specifying the ROC, if somebody writes like this, then this is wrong. This is correct if the sequence is right-sided sequences, or it is causal, then this formula is correct. If it is causal, then this will be correct. Okay, this will be a correct representation. On the other hand, if it is anti-causal, then you have to express this long divisions such that your quotient is a polynomial in Z. For causal, the coefficients are in the polynomial of Z inverse. If it is anti-causal, then then the polynomial in Z. If it is causal, polynomial will be in Z inverse, or you can say right-sided sequence, and here you can say left-sided sequence. Okay, we will illustrate this with the help of an example. Let me consider the simplest one, that is U of n. Now U of n is equal to, let's say, x of n. Therefore capital X of Z is equal to 1 divided by 1 minus Z inverse. But suppose the nature of the sequence is not specified, you are only told that x of Z equal to 1 divided by 1 minus Z inverse, then how will you find the inverse Z transform? Obviously there can be multiple answers if ROC is not given. The answer will not be unique unless the ROC is specified. Now this I can write as Z divided by Z minus 1. Now you take the long division Z, and here Z minus 1, substitute Z divided by Z minus 1. If you subtract, then it is plus 1. Right, so multiply by Z inverse, then it becomes 1 minus Z inverse. Then again subtract this, you will get Z inverse, and again you multiply by Z inverse, then this becomes Z inverse minus Z inverse. This is Z inverse square, right? Let's say this is Z inverse 2. Okay, this is Z, and this step is correct. Z minus 1. Okay. Then yeah, here I did a mistake. Now you multiply by Z inverse, so 1 minus Z inverse. This is correct. Then now this is Z inverse, and this is Z to the minus 2. And then again if you subtract this, 0 plus Z inverse, then you put Z to the minus 3, then this becomes Z to the Z to the minus 2 minus Z to the minus 3. So this is z to the minus 3, and like that keep on goes. Therefore the sequence will be 1 plus z inverse plus z inverse minus 2 plus z to the minus 3 plus and so on and so forth. So obviously the answer would be 1 comma 1 comma 1 dot dot dot. The zero sample is located at here. Therefore what is this? This is u of n. So that's how one can find the inverse z transform of the given function. Therefore the required sequence is u of n. Now what is the ROC of this? Obviously this series converges if mod of z inverse less than 1 or mod of z greater than 1, right sided sequence. Okay, the ROC is outside the unit circle. On the other hand, if I carry out the long division as it is, see the given function g of z is equal to 1 divided by 1 minus z inverse, right? Suppose if I do the long division as it is, what is going to happen? 1 minus z inverse, or let me rewrite this, minus z inverse plus 1 in this fashion. Now you multiply here minus z, then it becomes plus 1 minus z. Subtract, I'll get a z. Okay, then you multiply by minus z squared plus square, then z minus z squared. So this will go and z squared, and then minus I'm sorry, I should put here minus z cube, then z squared minus z cubed. Again this will go, this becomes z cubed, like that keep on goes. Therefore the sequence is minus z squared minus z cubed minus z to the 4 plus keep on goes. So this is sequence of you take minus commonly outside, 1 comma 1 comma 1 like this, and this is positive powers, so therefore minus, this represents u of minus n minus 1, left sided sequence. Therefore for this transform minus u of minus n minus 1 is a legally valid candidate. Agreed? So you must agree this also as one of the answers, and this seriously obviously converges for mod of z is less than 1. Therefore if g of z is specified with an ROC mod of z is less than 1, then you know it is the anti-causal sequence. Okay, when mod of z is less than 1, then it is anti-causal sequence. It is not, no, don't write u of minus n, okay, u of minus n minus 1, that is the correct, this is wrong. So the ROC is extremely important. The sequence itself completely will be changed. Okay, so let me take another example. This example is more interesting. X of z is equal to 2 divided by z plus 0.5 multiplied by z plus 1. Now ROC is not specified here, okay, ROC is not given. So they did not give the ROC. What to do in this case? Find the inverse z transform. Okay, suppose the ROC is not specified. How will you find out? Obviously, if the ROC is not given, then you will be having multiple answers. There will be multiple answers. First thing I do is write it as a rational function. First step is write it as a rational function in not z but z inverse. Therefore this is 2 divided by z plus 0.5 and z plus 1 is equal to, you multiply both the numerator and the denominator by z to the minus 2. So 2 times z to the minus 2 divided by 1 plus 0.5 z to the minus 1, 1 plus z to the minus 1. Now you see here the numerator degree was if you look at here in this expression, numerator degree is less than the denominator degree. The numerator the degree is 0, in the denominator degree is 2, therefore 0 is less than 2. But if you rearrange in this form, then the numerator degree is 2 and the denominator degree is 2, right? If you write it in a rational function in z inverse, the numerator degree is equal to the denominator degree. So whenever you have this type of condition, then this is called, as I said, improper partial fraction expansion. So whenever you have this type of cases, then you will be having a constant term k0, right, plus some other terms. Let's see what those terms are. And this constant obviously would be how much? It would be 4. How will you say that it is 4? By substituting z inverse equal to z inverse to go to infinity. Okay, so in this you substitute limit z inverse to go to infinity. Therefore 2 times z inverse whole divided by, you take z inverse here, 0.5 plus 1 by z inverse, and here you take one more z inverse, 1 plus z inverse, like this. So this z inverse, this is z to the minus 2. This numerator guy, this guy and this guy will get cancelled. Therefore limit z inverse to go to infinity, 2 divided by 0.5 plus 1 by z inverse, 1 plus z inverse. Sorry, this is 1 divided by 1 plus z inverse, I am sorry. 1 divided by 1 plus z inverse. Now this is equal to 2 by 0.5 plus 0, 0.0 plus 1 or 1 plus 0. 1 plus 0. So 2 divided by 0.5 becomes 4. Therefore you take the long division. The numerator I have 2 times z inverse. Yeah, this one. 2 times z inverse. And this side, if you multiply these two guys, the denominator, if you multiply these two guys, then you will get 0.5 z to the minus 2 plus 1.5 z to the minus 1 plus 1. Now you take 4 here. If you take 4, then multiply 4 this guy, then 2 times z to the 2, z to the minus 2. 4 times 1.5 becomes 6 times z to the minus 1. 4 times 1 becomes 4. Now it subtract. This guy will anyway go away. Minus 6 z inverse minus 4. Okay. Therefore, this becomes g of z is equal to, what is the constant term? 4 plus the numerator is going to be minus 6 z inverse minus 4, right, whole divided by the denominator term. The denominator is nothing but once again this guy, multiplication of these two factors, 1 minus 0.5 z inverse times 1 plus z inverse. Now it is as usual. So let's call this guy as x of z. Then as usual, okay, 1 plus a divided by 1 minus 0.5 z inverse plus b divided by 1 plus z inverse. Now you can find out a value and b value. If you now find out a value, then a is equal to minus 8 and then b is equal to 4. Therefore your g of z is equal to 4 plus 8 divided by okay, let me write 4 divided by 1 plus z inverse minus 8 divided by 1 minus 0.5 z inverse. So this is my g of z. I have simple pole. So we know the formula, alpha to the n u of n has the z transform of 1 divided by 1 minus alpha times z to the minus 1. So here what is the alpha value? 1 minus minus 1 times z inverse 4 minus or put plus and minus 8 divided by 1 minus 0.5 z inverse. This is my alpha here, and 4 becomes 4 times del of n, no problem. And this also you can use standard result, standard formula. Here also you can use standard formula. Now the question is, should I put u of n or u of minus n, or what should I put, whether it is right sided or left sided? How can I choose the ROC? Because ROC is not given in this problem. Okay, so in the inversion we have a problem. Suppose, let us assume the following case. Suppose the ROC is, let's say, if somebody comes and tell you the ROC that 0.5 less than mod of z less than 1. What do you mean by this? See, the ROC is bounded by the poles. If you plot it, let's say this point is 0.5 and this one is 1. Now the ROC is outside of this circle, inner circle, and inside of the outer circle. So outside of the inner circle, so whenever the ROC is outside of a circle, then the sequence is right sided sequence. Yes or no? That's what we said in the previous lecture. So the ROC is outside of the inner circle. Whenever the ROC is outside of a circle, then that sequence is right sided sequence. Therefore this is going to be 4 times minus 1 whole to the n u of n, right sided sequence. Now this is the location of 1 outside circle. This is 1 and this one is 0.5. Now the outer circle has a radius of 1, but the ROC is within the outer circle. That means inside the circle. Whenever the ROC is inside the circle, then the sequence is left sided sequence, anti-causal sequence. Therefore this guy gives anti-causal sequence, that is left sided sequence. Therefore this is equal to minus 8 times minus 0.5 whole to the n u of minus n minus 1, because of the left sided sequence. So, and what about this guy? This 4 becomes 4 times del of n. So this is my g of n. That's it for the given ROC. For this ROC, this is the inverse Z transform. So this part will give you anti-causal sequence, because mod of Z is less than 1. and this will give you a RSS, right sided sequence, or causal sequence, because mod of z is greater than 0.5 here, mod of z is greater than 0.5. Therefore mod of z greater than 0.5 indicates a right sided sequence, and mod of z less than 1 indicates left sided sequence. This is a left sided sequence and this one is right sided sequence. In case, let us okay, okay, this is one condition. Okay, minus 8 minus 0.5. Where did I do the mistake? Oh, I am sorry. Okay, I am very sorry. I am very sorry. Confused you. Just a minute. I did a mistake. I'm sorry. Now, what is the pole? Pole is 1 here. And what is the pole here? Pole is 0.5. So the inner circle is 0.5 radius. So this is my pole. This is my circle. So therefore the ROC is outside of the unit circle. So it is this one is a right sided sequence. Okay, and therefore one second, hold on. I did a small mistake. Confused. Okay, so this 4 is nothing but it becomes 4 times del of n. Then this one, if you look at this guy, the pole is 1 and the ROC is inside of this pole, therefore this is going to be plus 4 times minus 1 whole times n. U of inside means left sided sequence, therefore minus n minus 1, anti-causal sequence. What about this guy? 0.5, but my ROC is greater than 0.5, therefore this is right sided sequence or causal sequence, therefore minus 8 times minus 0.5 times n to the n u of plus n. That's it. So for this given ROC, this is the equation. So this is the inverse Z transform, G of n. That's all. I did a mistake, I'm sorry. Okay, now let me take the case 2. If the ROC is something different from the previous one. Let's say the ROC is mod of Z is less than 0.5. Now is this possible? This is 0.5 circle and this is 1 circle. Now this is my ROC. Now the question is this possible? Why not? This is possible because the ROC does not contain any poles. As long as it doesn't contain any poles, absolutely no problem. But the ROC is inside the unit circle. Inside the circle of radius 0.5. Therefore, this is anti-causal sequence. Anti-causal or left-sided sequence. So both the guys are left-sided sequence. Therefore, your G of n is going to be 4 times del of n plus 4 times minus 1 whole to the n, u of minus n minus 1 minus 8 times minus 0.5 to the n, u of minus n minus 1. Now what is the other possibility? ROC mod of Z greater than 1. Can I write like this? Yes. So in this case, again you have two poles, one pole at 0.5 and another pole at 1. So you have like this. Now the ROC is outside the unit circle. Therefore, this represents a causal sequence. Causal sequence means right-sided sequence. Therefore, in this case, your g of n is equal to 4 times del of n plus 4 times minus 1 to the n u of n minus 8 times minus 0.5 to the n u of n. You see there are three possibilities. Now let me take case 4. ROC mod of z greater than 0.5. Now is this ROC possible? Possible. Let me check whether it is possible or not. This is 0.5 and this is 1. So your ROC says greater than 0.5. So this is my ROC like this. Now if you look at here, the ROC contains a pole. There is a pole, right? But as per our definition, the ROC should not contain a pole. If the ROC encounters a pole, then the function will not converge and there is no Z transform, right? The Z transform will not exist. So the important point is the ROC must not contain the pole. But in this condition, the ROC contains a pole. Therefore, this is not at all possible. So this cannot be the ROC. Cannot be the ROC. Okay. So this possibility will not exist because the ROC must be bounded by poles. The ROC must not contain a pole. It must be bounded by the poles. Therefore, this condition is wrong. Okay, the poles are at minus 0.5 and minus 1. So the ROC can be outside this circle and inside this inner circle, that is annular region. So we have exhausted all the possibilities. Therefore, the fourth possibility will not be possible, will not be valid. Therefore, there are three answers. If the ROC is not given, then this is one correct answer, then this is also one correct answer, and this also another correct answer. So unless the ROC is specified or unless the nature of the sequence is specified, you cannot evaluate correctly. That is, if the sequence is totally causal, then you have one answer. If the sequence is anti-causal, you have another answer. If it is mixture of two, that is, if it is combination of causal and non-causal, then you have the third answer. So this example illustrates the importance of the ROC in specifying a Z transform. So if you don't specify the ROC, then you cannot find your unique Z transform, or you cannot find your unique inverse Z transform. Okay, so I think this is a time to stop. So that's all about inverse Z transform, and in the next lecture let us talk about some properties of Z transforms. Okay, exactly like those of the discrete time Fourier transform. Okay, so let me stop. Thank you very much.